So I'd like to thank Dr. Richard Bouchard for an introduction to photoacoustic imaging and some salient features of this technology and examples. I'd like to build off of Dr. Bouchard's presentation by discussing some recent photoacoustic imaging applications for interrogating tumor. So first, here's my conflict of interest slides. We work with a number of companies, collaborators, and have some funding. So, photoacoustic imaging is also known as multispectral optoacoustic tomography, or MSOT. I'll refer to this technology as MSOT for this presentation. An MSOT is not a good anatomical imaging modality, as can be seen on the top of this slide. It can be challenging to find the organs, but with some training, you can identify those features in the mouse. However, it is a very good molecular imaging technique. You can identify molecules such as melanin, hemoglobin, and oxyhemoglobin, as well as exogenous contrast agents. And really, the key is the word multispectral. A single image at one wavelength doesn't provide much information, but by collecting multiple images at multiple wavelengths, then spectral unmixing can be used to isolate the dye to image the dye. In this case, indocyanine green, which was validated with epifluorescence validation after the in vivo imaging. This is a study done by Vasilis Nitristos and his colleagues in 2010. Really nice example. So we've been performing dynamic contrast enhancement MSOT to evaluate vascular perfusion in tumors. Here's a tumor image taken with the MSOT. And by detecting the signal at 680 nanometers, we can then follow the uptake of GenHan 680, a fluorescence dye that also can be used for MSOT. And we can watch that flow into the tumor. And we can also identify an arterial input function or a blood vessel that has rapid uptake and then washout of GenHan 680. And this is an advantage of MSOT relative to MRI because we can measure or identify spots where there is high hemoglobin signal, and therefore we can identify the blood vessels very easily. And that can be a challenge in MRI. So we can take this data that has dynamic uptake in the tumor and, of course, in the arterial input function. And if we could turn that into a concentration from signal to concentration, then we could do standard pharmacokinetics analysis and measure K-trans and KEP just like in DCE MRI. Fortunately, there's a problem here. The conversion of signal to concentration is hampered by the fact that the intensity of the laser a light that reaches every point within the tissue is different. There's a fluence issue, variable fluence throughout the tissue, and it is depth dependent. So it's challenging to relate to the signal to concentration. We've worked around this problem by combining the optoacoustic signal model with the two-compartment model from DCMRI to create what we call K-app, an apparent wash-in rate of the agent. You still get the same washout rate, surprisingly, from this. So we measure a KEP. And here's a study where we had a tumor model that had low hypoxia, medium high, another model that had medium hypoxia, and a third model that had high hypoxia. First two are pancreatic tumor models. The third was a colorectal tumor model. And we measured KAP and KEP before and after applying 10 gray of radiation. And you can see that the results for the wash-in rate show that the normoxic tumor was affected by the radiation as expected, and there was a significant drop in this perfusion. The mildly hypoxic tumor model saw a mild drop, and the hypoxic model, which should not be affected by radiation therapy, oxygen is needed for radiation therapy, we actually saw an increase in the vascular perfusion. And now we have a hypothesis that this is caused by having some holes blown in the blood vessels very temporarily by the radiation, but not enough to cause permanent damage. Now, those holes can be sealed up and the tumor can continue to grow normally. And we've seen this in other studies from years ago using anti-angiogenic agents. Yeah, in this case, oh, and by the way, the KEP parameter, the washout parameter, really did not provide much information in this study because indocyanine green is a hydrophobic dye and it just doesn't wash out of the tumor very well. But the key is that if we see a large decrease, a small decrease, or even a large increase, well, that could then indicate how to change therapy. Perhaps there would be just a continuation of the treatment all the way to actually applying an anti-angiogenic agent to reduce this blowing of the holes in the blood vessels and subsequent repair. I'd like to talk about a slightly different technique, oxygen enhanced, or OE MSOT, to measure delivery hypoxia, how much oxygen is being delivered to the tumor. And we first measure the oxy and deoxyhemoglobin signals under the presence of 21% O2, medical grade air. And then we switch to 100% O2, waiting some time for equilibration of the mouse. And then we measure those parameters again. So we get an image set, we can do spectral unmixing and measure this percent SO2. It is dependent on spectral coloring, other features that cause the laser light to have different amounts of energy deposited at different depths. So I should acknowledge that it's not a perfect measurement of percent SO2, but it does a pretty good job, as you'll see. So we can get percent SO2 under medical grade air and 100% O2. And it's an interesting idea that you can actually see that there is a difference in this percent SO2 with these two types of carrier gases. And this is known as delta SO2, really championed by Sarah Bondic at Cambridge, and also Ralph Mason at UT Southwestern has done a very nice job really originating this idea as oxygen as a contrast agent. So we can measure delta SO2. And this is challenging to interpret, but our interpretation is that this is showing how much more oxygen gas or oxygen capacity is available in a tumor. It's as if you're driving down the road and you look at your gas tank and you can see that your tank is only 1/4 full. Well, it's also 3/4 empty. You have 3/4 of that tank that have capacity for more gas. So this is showing us that if we were to flood the tumor with as much oxygen as possible, 100% O2 carrier gas, what is the capacity to take up more oxygen? Well, here's the data prior to and after treatment. Here's the plots of the data as well. I'm going to do this in the interest of time and just focus on the results of these data sets. In fact, I'm going to make it more simple and show that yes, we can determine the difference between normoxic, mildly hypoxic, and hypoxic tumors using either of the gases, 21% O2 or 100% O2. Also, the delta SO2 then also shows which tumors are normoxic and hypoxic. So this is a prediction biomarker. We can tell before applying radiation therapy which tumors are normoxic and which ones are hypoxic, and therefore how well the radiation therapy should work. Unfortunately, the percent SO2 doesn't really show a pattern with either carrier gas after radiation therapy. So this is not a post-treatment biomarker. This is only a prediction biomarker before starting treatment. However, the change in delta SO2 clearly shows that the normoxic tumor changed its oxygen or ability for oxygen capacity after radiation therapy. The mildly hypoxic tumor changed somewhat, and there was no change within the hypoxic tumor. In other words, the hypoxic tumor is a hypoxic. It doesn't have any capacity to take up more oxygen when you give it 100% O2, and that really didn't change with the therapy. We didn't cause any therapeutic effect. The normoxic tumor does have much less capacity to take up more oxygen. So this combined measurement along with the DCE MSOT can be done in a simple scan session that's approximately half an hour long. There's some prep time and some cleanup as well, like all other small animal imaging studies. But you get two measurements for the price of one, and actually three if you count the delta SO2 as a third measurement. So we're really enjoying this technology in our lab, and I like to make the provocative statement that I think someday DCE MSOT, along with OE MSOT, can replace DCE MRI and bold MRI as a preferred method for interrogating small animal models. So with that, I'd like to stop and just thank the group, especially Sheree Goyle, who was instrumental in getting this to work. Also, Jorge de la Cerda and Bill Schuler were also very important for supporting this work as well. And I'll stop there. Thank you.